glad to know that that's CD you get that has Ed's video on it. It'll be great. It'll be you'll have the first copy before it goes viral on YouTube, just like Justin Bieber's internet. So you can say this is the first to own it. So the real question is, how many people here know who Justin Bieber is? That's the bigger question. Yeah, if you have kids in the junior high or you have grandkids, then you probably know who Justin Bieber is. Okay, so let's get started. Simulcast, we're going to talk about narrowband a little bit. We're going to talk, some of this is also just related to narrowband in general, not just narrowband simulcast. So let's talk a little bit about why simulcast, because we still get people occasionally will call up and say, well, why should I implement a simulcast system? And my first comment is, well, have you tried to get additional channels for all these other sites that you want to provide coverage? Usually the answer is, well, we can't get any additional channels. So then that leads you around into the conversation about why you want to use simulcast, because it is a spectrally efficient technology. Particularly if you're in a rural area that's near an urban area. If you're way out in the pucker brush somewhere, you know, like maybe you're in Wolf Point or Williston up there in North Dakota or Montana, you might be able to get channels. But, well, probably not there actually because you have the Canadians, but you know, someplace maybe out in the middle of Wyoming, well, you probably can't get them there either because they used them all up on their simulcast, on their statewide system. They had to use marine frequency. So, see, no matter where you go, you can't get channels. So, it is a spectrally efficient technology. And it's also coupled with receiver voting, which is a big boost on portable talking. You know, it always amazes me that people still go out and buy 100-watt mobile radios and then give their officers 5-watt portables and then want the portables to work everywhere the mobiles do. Well, you might as well buy 5-watt mobile in that case, because 100-watt mobile is a bit of overkill. And also now with the modern technology that's available, it's a lot easier to maintain than for any of you that have done simulcast for many years. A couple things about narrowbanding, and remember, I've seen signs everywhere about this. December 31st. 2012 is the last day for wideband operation. We've been telling people 2012 because as soon as you tell them January 1st, 2013, they think December 31st, 2013, they have a whole another year. You tell them 2012, they go, oh my gosh, that's next year. So, you know, we've already missed our budget cycle. So, you know, we're already 2 years behind in the process. Currently, no new wideband systems can be licensed, and the FCC has had several seminars that has reinforced the deadlines. There really hasn't been a clear, at least that I've seen anyway, unless somebody else has input from the enforcement division of the FCC, exactly how they're going to enforce all this, but they have been pretty clear that they're not really interested in delaying the deadlines, because this has been going on. If you go back to the original Part 88 rewrite, this is going back to the early 90s, so this isn't new news. And conversion from wideband to narrowband could be a big deal or not. It really depends on your location. I've had some people say, hey, we converted to narrowband, no big deal. Don't even notice the difference. I've had other people say, we converted to narrowband and we had to add 4 or 5 floating receivers, we had to add to the transmitter site, and the users aren't happy with the audio performance. So the big deal here about narrowband is that the signal levels required to deliver the same audio quality are higher. We have a lot of people say, well, I got a 100-watt transmitter right before narrowband, a 100-watt transmitter after narrowband. If I go out here, you know, 15 miles away, stand out in the field with a service monitor, I still measure the same, you know, whatever the number is, minus 90 dBm, right? So why is my coverage going to change? Well, it's not your RF signal level that's going to change, it's your delivered audio quality, and it can be significant. In addition, all aspects of your radio system operation and maintenance are more critical because now you're dealing with a lot smaller levels. You know, it's bad enough when you get 5 kilohertz deviation, now you're talking about 2.5 kilohertz deviation. You know, the officer is not speaking into the microphone. Now, you know, the old systems did not speak, they're probably deviating about 1.5, maybe 2 kilohertz. Well now, if you put in a narrowband system, they're not speaking. Same audio level now is maybe 400 or 500 hertz of deviation. It really makes a significant difference. There are specifications vary widely between brands and models. And in fact, some radios that had a top-of-the-line receiver performance at wideband, when you look at their narrowband performance, it's mediocre. And some radios that had sort of mediocre performance in wideband actually have better performance in narrowband. So you can't say, well, I always buy, you know, the top tier level, whatever it is, and assume that that's going to be okay. You really have to to check the specifications of the radios, and you might find yourself surprised. The other thing is audio speech processing can make a difference. We've used an outboard speech processor. It has one that's available for sale, but there's several others around to put in the transmit audio line to boost the low levels of speakers. You got to do it correctly, otherwise you end up just amplifying all the noise. But there are some semi-intelligent speech processors out there that aren't terribly expensive and actually really do help on narrowband systems. So narrowband simulcast, well, it's just like wideband simulcast, but everything's more critical, less tolerance. So your deviation settings, your audio level settings, all of that stuff are more critical. Frequency stability, though, nowadays, I don't think anybody's still using ovenized oscillators for anything. So your GPS oscillators are perfectly, are going to give you all the frequency tolerance that you need. The big issue, though, is that the receiver capture effect is less with narrowband. We'll talk about that in a minute. We've actually done some measurements on some radios, and the capture ratio is about 15 dB. So for most wideband radios, it was kind of in the range of 10 dB. And so this has a significant impact on your simulcast overlap area, how large of an overlap area, or how large of an area you have to consider as your overlap area, because the radios won't discriminate between the two simulcast sites as well as they used to. So you'll see in a minute, we'll talk about, I got some coverage predictions here, we'll talk about what that actually means. And again, the problem is that capture ratio is brand new. So, 5 years from now, well, 5 years from now, maybe everybody will be digital, but 5 years from now, a couple years from now anyway, and you have all the new radios out and everybody is pretty much narrowband only, the performance specifications for the radios may be optimized a little better for narrowband, but right now it's a pretty wide variation out there, but you really should use 15 dB for your capture ratio. So here's an example, coverage and delay interference, wideband versus narrowband. Now this is a project that we implemented a few years ago. This is an 11-site simulcast system. All the sites are low, well, almost all of them are low. And we went in and calibrated to do this project to convert to narrowband, which we're still in the process of doing. We went in and actually did a bunch of signal level measurements to actually calibrate our prediction model, and so we could see where it was, where it was off. And if you look, away from the picture here. Right along in here, you'll see all this black areas. These are areas that exceed the delay tolerance. And for this is wideband, so this is 10. This is 10 dB. And right along this area here, and if you talk to the client and you do drive testing, we find that this actually fairly accurately predicted where the delay interference is. And as you can see here, in the coverage areas, the yellow coverage areas are areas where you have better in-building coverage. And so you can see this is pretty much is how it performs today. This is actually a pretty good representation. Here's what happens when you convert to narrowband. So you can see that, number one, the coverage is reduced significantly. So this is kind of a big issue here for them. And this is talk out coverage. So you can see that, like I said, the coverage is reduced pretty significantly. But what's worse here is you can see in these areas, the simulcast overlap has increased significantly. Now, this design has not been optimized. So this is, this was just to see, okay, what kind of a problem are we going to have if we keep everything the same? So we've not, applied antenna patterns. We've not, tweaked delays or any of that sort of stuff for this. But this shows you that, in the basic sense, you can see that there's a pretty significant increase. Now, some of this over here we don't really care about. This is out in Puget Sound. This is all water. So unless they're doing a marine rescue out there or something, but this area in here is this is a major highway that goes north and south through the county. And right now, that has a little bit of simulcast overlap distortion, but you can see it gets significantly better or worse in down there. So this is, and we're actually going to take one of their channels and convert it to narrowband and see how well the modeling matches. on this particular system, see how well the modeling matches the prediction. In the past, we found that it's pretty accurate. So using these numbers. So we're anticipating that, we're trying to figure out what to do about it. We'll probably have to add a site. We might be able to do some things with antenna patterns. You know, the big issue for them is really right in here, and then this is kind of a bad area as well. So we're going to cover deal with that exactly. So one of their alternatives they thought was, well, let's put a P25 and let's see what would happen. So a couple of things when you go digital. Number one is that to some degree the chart that you always see, where analog falls off and by the end it's all noisy and the digital works perfect till the very end, right? Well, to some degree that's a correct chart. I mean, assuming you're doing it in the lab and you don't have a lot of other sort of propagation effects, or you're in a relatively flat terrain area. When you try to do that in some other areas where you have a lot of multipath and bounce and you're doing it with simulcast, you get some kind of different effects. But you can see you do end up with some better audio recovery levels in signal levels. So with P25 here, you can see that the coverage has stayed pretty well, but you still have a lot of simulcast overlap distortion. And phase one in particular has fairly poor, maybe poor is not the right word, but it has fairly limited delay tolerance for simulcast, or for any multipath for that matter. So in phase two, at least according to everything we've heard so far, actually has better simulcast overlap delay tolerance because of the modulation technique that's being used. So the initial numbers, of course, nobody's actually really got a system running yet. Maybe not full bore out with lots of experience. So phase two stuff is so a little bit of a swag. But you can see that going to phase two, because there's a little more simulcast delay tolerance ability here, that phase two would actually provide better performance. But there's really not anything you can do with that yet.